students, this is Dr. Aisha Nazuk here. Today we are going to start our fourth video lecture for the course Introduction to Econometrics. So those of you who haven't watched the earlier video, it's strongly advised that you watch the other videos in this playlist, and then you can start this video, which is the fourth one. But if you happen to have the background concepts already and you want to cover the contents of today's lecture, you are more than welcome to start from this video. So the contents of this lecture are different mathematical representation of the regression betas, proof of linearity of regression betas, then derivation of the variance of regression betas, and standard error of regression. So these are the contents, and this lecture is focused or based on chapter 3 of Gujarati and Porter book 5th edition, which is easily downloadable from the Genesis library. I have posted a video on downloading books from the Genesis library. So if you don't know how to use the Genesis library, you are more than welcome to watch that video and download the Gujarati and Porter book from Genesis library. So this lecture is focused on chapter 3 of Gujarati and Porter book. So let's start today's lecture. In the last video lecture, we were discussing the OLS, or the ordinary least square estimation method, where we discussed different algebraic derivation of the OLS betas or the regression betas, and then we derived the formulas for the slope and the intercept coefficient. So given a regression equation, by now it's quite clear that the two important parameters are the intercept and the slope coefficient. So we derived a formula for the slope coefficient, which is different from what's being displayed here in equation 3.1.8. So let's see how this form is equivalent to the formula that we derived earlier on. So if you haven't, you don't have by now a clear idea of which formulas I'm talking about, kindly watch video number 3 first and then start the video number 4, which is this video. So the slope coefficient is given to be equal to sum of lowercase xi or the small xi and small yi. By now it's clear that whenever I write a variable in lowercase form, that means this is a deviation form. As you can see here, sum of xi square, for example, this is equivalent to saying that sum of capital Xi minus x bar whole square. So whenever I write something in a lowercase form, that means that it is in deviation form, or that the mean is subtracted from the actual values. So if I look at these three equivalent formulas, let's see how they are equivalent. If you consider the denominator of the first formula, which is sum of lowercase xi square, this is equal to sum of xi minus x bar square, which is simply the definition of lowercase xi. So if I apply the square formula, you know that a minus b whole square is equal to a square plus b square minus 2 times a into b, and then I apply the summation inside. So if I expand this by using the formula of a minus b whole square, it's very easy to say that this is equivalent to sum of xi square, because this is basically a square and then the summation is applied. And then we have minus 2 times a into b and the summation is applied. A means the first term and b means the second term, and then plus we have the second term square, or the b square, which is sum of x bar square. So now let's see how I can further simplify this. So sum of xi square as it is minus 2 times x bar. You know that x bar means mean of x, which is a constant, so I bring it outside the summation sign and then I apply summation just on xi. So I have this minus 2 times x bar times sum of xi plus sum of x bar square. Once again, this x bar square means a square of a constant, which is again a constant. So I will actually this sum of x bar square will means n times x bar square, because this is a summation of a constant, and you know that summation of a constant is equal to n times that constant. So here the constant is x bar square, so this term, the last term, is actually n times x bar square, right? Similarly, sum of xi, you know that sum of xi is equal to n times x bar, right? By the way, let me show some formulas here that will make it further easy to understand. So these were the useful formulas that are being used in that derivation. You know that sum of a random variable xi, when it is summated from 1 till n, is basically equal to n times x bar, because you know that by definition x bar, or mean of x, is sum of xi values divided by n. So this is the reason that whenever some variable is summated from 1 till n, you can equivalently write it n times x bar. Similarly, sum of xi square could be written as n times x bar square. So these are the concepts that are being used here in this derivation. So we were here, so that means that if we use this equation, sum of xi square, this is, you can say, as it is. Or if I start from this equation, let's see, sum of small xi square is equal to what's written. It is equal to sum of xi square, which is the first term here. Then we have minus n times x bar square. How is it being derived? The second term, sum of xi, is basically n times x bar. So this becomes, we have an x bar here already, so this becomes minus 2n x bar square, plus this becomes n times x bar square. So n times x bar square minus 2n times x bar square becomes n times x bar square. So sum of xi square is equivalent to saying sum of capital Xi square minus n times x bar square. So we have this second form which is written here. So the numerator is settled. Now we have the denominator is settled, and now we have to settle the numerator part. So what's written here, that whether we write small xi and small yi, it is equivalent to writing small xi and capital Yi. So let's see how is that possible. So let's start from sum of xi yi. We know that sum of xi yi is equivalent to saying, if I write yi in its full form, it's the deviation yi minus y bar. So let's multiply this xi inside. So we have xi yi minus y bar times xi, right? So which is equivalent to, if I actually I just want to remember that I want to prove that sum of xi yi, that is small xi small yi, is equal to sum of small xi and capital Yi. So we have to actually vanish this second term. So if I write this y bar as it is, and xi is in its full form, that is the deviation form, xi minus x bar. So we know that sum of deviation taken from the mean is always 0. So this term reduces to 0, and we are left with sum of xi and capital Yi. So this is how the full second equation is settled. Now the third form is on the similar logic. So now I leave it on your understanding. Use the concepts learned so far and the algebraic manipulations that we have shown here in this slide. Use these and you can derive the third form for beta 2 hat as well. Next we prove the concept of linearity of OLS beta. Remember that we said that in econometrics a linear regression means that the parameters are linear. So let's mathematically prove that the beta 2 hat and beta 1 hat, they are linear. So let's focus first on beta 2 hat. So we have just derived this form of the formula of beta 2 hat, which is sum of xi capital Yi over sum of xi square. So if I call this part xi over sum of xi square as ki, let's call these some weights, so then I can write beta 2 hat is equal to sum of ki times yi. which means now you can easily see that this becomes a linear function of yi, because these ki are simply the weights. So beta 2 hats is equal to sum of some weights multiplied by yi. So that means that this is a linear function of capital Y. So similarly, it's very easy to show that beta 1 hat, that is the intercept, is also linear estimator. So once again, I leave it on your acumen to try and prove that beta 1 hat is also linear estimator. Let's note some of the important properties of Ki, which will be very useful in some derivation that we'll be doing shortly. We know that in a regression setup, the independent variables or xi are assumed to be fixed. As we started the classical definition of the ordinary least square, we said that the xi are fixed factors. So since the xi are fixed factor, or technically speaking non-stochastic, so the ki's are also non-stochastic, that is, these are also fixed values, and this is the reason we said that sum of ki yi means sum of some fixed weights multiplied by yi. Then the second property is that the sum of ki is 0, which is very easy to prove. For example, if you see sum of ki means sum of xi over, I've just switched in the values of ki, which is equal to sum of xi over sum of xi square, and you know that this sum of xi is the sum of deviations taken from the mean. So this becomes 0 and sum of ki is proved to be 0. Then sum of ki square is equal to 1 over summation xi square. You can simply prove it by taking the square of this equation, and you can easily derive this result. Similarly, result number 4 is also very straightforward. Sum of ki xi is equal to 1. That is, if you multiply this whole expression by xi, then the resultant answer will, and take the summation, then the resultant will be 1. So these 4 properties will be very useful in some of the derivation that we'll be doing. So it's better to by the way, remember these, that sum of ki is 0, sum of ki square is 1 over sum of xi square, and sum of ki times xi is 1. So let's prove that beta hat is an unbiased estimator of population beta. In the previous slide, we just proved that the betas are linear. Now we are proving that the betas are unbiased estimator of corresponding population beta. So if we have the slope coefficient beta 2 hat, we just derived this formula, which is equivalent to saying sum of ki times yi. So we know that the population regression function is yi is equal to beta 1 plus beta 2 times xi plus ui. So if we switch this population regression function in equation number 3, we can write that beta 2 hat is equal to sum of ki times this full value of yi from the population regression function switched in equation number 3. So then we multiply this ki inside, and we know that beta 1 is a constant, so I bring it outside the summation sign. So beta 1 times sum of ki plus beta 2 times sum of ki xi plus sum of ki ui. So now you know that we just proved that sum of ki is equal to 1. So this beta 1 times sum of ki, sum of ki, we proved that it is 0. So the first term vanishes. And we note in property number 4 that sum of ki times xi is equal to 1. So this second terms become beta 2 multiplied by 1, which is like beta 2. And then the third term sum of ki ui, and I have written it as it is. So this equation reduces to this one. Now we will apply expectation on this, and we will prove that expected value of beta 2 hat is equal to beta 2. So applying the expectation sign on both sides, we have that expected value of beta 2 hat is equal to beta 2. As I said that beta 2 is a constant, so expected value will not be applicable on it, because we know that expected value of a constant is a constant itself. So expected value of beta 2 hat is equal to beta 2 plus sum of ki times expected value of ui. You see, expected value is not applied on ki because we just said that ki are non-stochastic, that they are fixed values, right? Because x's are fixed vectors, so ki's are also fixed weights. So the expectation is only applied on the random error part, which is a variable, and we know that this is a classical or a crucial assumption of the regression, that the mean or the expected value of residual is 0. So that's why this equation reduces to expected value of beta 2 hat is equal to beta 2, which completes the proof that beta 2 hat is an unbiased estimator of beta 2. Similarly, we can prove that the intercept, sample intercept, is an unbiased estimator of population intercept. So we know that the formula for intercept is y bar minus beta 1 times x bar. So I have just switched the values of the formula for the intercept, and then we apply the expected sign. And what is y bar? You know the value, the population regression function. Let me show that once again here. So this is the population regression function. If I apply y bar, that is I take mean on both sides, so I am left with y bar is equal to beta 1 plus beta 2 times x bar, because u bar will be 0. So using this result, so y bar beta 0 plus beta 1 times x bar and plus u bar. For now I haven't put it exactly equal to 0. Once I apply the expectation, I will make it equal to 0. Then minus beta 1 times x bar. Then I apply the expectation. Expected value of beta naught is the beta naught itself, and then I apply expectation on when I apply expectation on u bar, we know that expected value of the residual, that will become 0, so this part will vanish and we will be left with taking x bar common from these two terms, and we'll be left with beta 1 minus beta 1 hat times x bar. So we just proved that beta 1 is an unbiased estimator of beta 1 hat. In other words, actually this is sort of a little bit of, you can say, a notational issue. When I write here beta 1, it's actually the slope coefficient, which in above derivation was written as beta 2. So please don't be confused. This simply means expected value of slope minus the slope hat. So this we just proved that it is equal to 0. Why is it equal to 0? Because expected value of beta 1 becomes, expected value of beta 1 hat, this becomes equal to beta 1. So that is why this term will become 0 and we will be left with this term only. So this proves that intercept is an unbiased estimator of population intercept. Next we do the proof of the variance of OLS beta. Here we start with the basic definition of variance. We know that variance of a random variable is equal to expected value of that variable minus the mean of that variable and then whole square. So beta 2 hat and expected value of beta 2 hat, we just proved that it is equal to beta 2. So this equation is reduced to this form. Then we wrote that beta 2 hat in the previous slide in equation number 4, we just derived that beta 2 hat is equal to beta 2 plus sum of ki ui. So I use this value, so beta 2 hat minus beta 2 will be equal to this term, sum of ki ui. So this is exactly, I have used the equation number 4 here in step number 3. Now this is actually, if for a moment I ignore the expectation sign, this is sum of you can say weights multiplied by variable and then square. So for example, if we had only two values of k and I expand this summation, it would have been k1 times u1 plus k2 times u2 whole square. So if I simply apply the formula of a plus b whole square, this becomes k1 square u1 square plus k2 square u2 square plus 2 times k1 times k2, and then there should be something written here as u1 and u2 as well. So let me make this small correction here. Yeah, so k1 u1 plus k2 u2 whole square is equal to k1 square u1 square plus k2 square u2 square plus 2 times the first term into second term, which is this form. So actually we have the square of the terms and then the 2 times the cross product. So this is what is written here, that once we expand this, we can imagine that this will be sum of all the square terms and then the cross products. These cross products will actually, once we apply the expectation, the cross product will become 0. Why? Because by definition we said that different values of the random error or the residual term, they are 0. That is, expected value of ui and uj is 0, which is the, you can say, from the structural definition of the residual term, because residual term or the ui series is assumed to be random, and there should not be any correlation between subsequent values. So if we have two different random values, there should not be any correlation between the random values or the residual of those two values. So expected value of ui and uj becomes 0. So as a result, the cross product term, once the expectation is applied, the cross product term becomes 0. So now consider the square term. So this is expected value of k1 square times expected value of u1 square. We know that by the assumption of no heteroscedasticity, or in simple terms that the variance of the residual series is fixed and it is equal to sigma square. So this will become k1 square times sigma square plus k2 square times sigma square, and so on. So we can take sigma square as common and sum of ki square as the sum of all these squared weights, that is k1 square, k2 square. So variance of beta 2 hat reduces to this equation. Right, now by simply using the definition of ki square, let me refer back to some previous slide. So sum of ki square according to the third property is equal to 1 over sum of xi square. So we are using this third property here, and sum of ki square 1 divided by sum of xi square. So variance of beta 2 hat becomes this expression. Similarly, we can find the variance of beta 1 hat as well, which I leave to you just to try based on the concepts and the algebraic details that you have learned so far. You can easily derive the variance of beta 1 hat, that is the intercept of the OLS. Now there are some useful notes that will be used in the upcoming derivations. Recall that the sample variance is an unbiased estimator of the population variance. It means that if we are using a sample data and we want to give an unbiased estimator for the population variance, then if I use this formula for sample variance, then researchers have proved that this formula gives an unbiased estimator for population variance. If you wish to see detailed explanation on this, which is not directly required in this course, but if you, out of curiosity, you want to try, you can take a population and draw all possible random samples and take the calculate the variance using this formula of all the variances, and then average out all the variance values, and you will see that average of all the variance values, sample variance values, will be equivalent to the population variance. But as I said, this is not directly relevant. Why am I telling it here? That in some upcoming slides this concept will be used. So why this is an unbiased estimator? If you look at the numerator, this deviation xi minus x bar square, if I relate it with the population mean, had this been population variance formula, this should have been equal to xi minus mu whole square. As you note that the population mean is represented by the Greek symbol mu. So instead of mu in the numerator we are using x bar. So actually we are, you can say, we are approximating mu or the population mean by the sample mean. So that is why we are dividing by n minus 1, which is the sample size minus the number of unknown parameters. So here population mean mu is an unknown parameter in this formula which is being approximated by x bar. So why is it important? You will shortly understand. Next we discuss the concept of precision or standard error, which is simply directly linked with the variance formula that we have just derived. So we just derived the formula that the variance of beta 2 hat is equal to sigma squared divided by sum of xi squared. So if I take the square root of this formula, then we call this as standard error of beta 2 hat, which means sample to sample expected variation in the value of beta 2 hat. Remember that we are dealing with one random sample. So the value of beta 2 hat that we get from a random sample is a single value. So standard error gives an estimate that had we taken some other sample, what is the expected variation in the values of beta 2 hat. So this is called the standard error of beta 2 hat. Now this sigma or the population variance, this is often approximated by using this formula that the estimate of sigma is called as sigma hat, or simply you can say an estimate of sigma square is called sigma hat square, which is sum of residual square divided by n minus 2. So why am I now dividing by n minus 2? Because if you look at ui square or the residual square, it is equivalent to writing yi minus beta naught hat minus beta 1 hat times xi. So here the number of unknown parameter, that is beta naught hat, is an estimate of beta naught, beta 1 hat is an estimate of beta 1. So here we have two unknown parameters, therefore sigma hat square is equal to sum of ui hat square divided by n minus 2. This is an unbiased estimator for the population variance sigma square. Then there are some alternative representation of the same formula, or you can say that alternative expressions for the sigma hat square. I leave it to you to try out these different equations that are given here, and you can simply derive one equation by using the other. So talking about the sigma hat that we just derived, if we take the square root of this sigma hat square, if we take its square root, the resultant thing is called the standard error of estimate or the standard error of regression. This is actually a measure of goodness of fit. So lower the value of standard error, higher is the precision. That is, its value is used as a yardstick for deciding how good a model is, or how perfectly a model has been able to explain the dependent variable. So if this error is lower, or the standard error of the regression is a low value, then the model is a best, you can say better fit for a given dependent variable. We will discuss this concept of standard error of regression in detail in later videos. Now some of the important features of the variance of beta 1 hat and beta 2 hat. Let me show for once the formula for beta 2 hat. If you see, the formula is variance of beta 2 hat is equal to sigma square over sum of xi square. That is, sigma square is directly linked, whereas sum of xi square is inversely linked with beta 2 hat. So exactly this is what is written here, that variance of beta 2 hat is directly proportional to sigma square but inversely proportional to sigma xi square. That is, if sigma square is a constant value, as we just said that the variance of the residual term is a fixed value, by using the assumption of homoscedasticity. So if it is a given value, then larger the variation in x values, the smaller the variance of beta 2 hat. Why? Because sum of xi square, this is in denominator. So if this is a high number, beta 2 hat or the variance of beta 2 hat will be a small number. And we know that when variance of something is small, it means it has a greater precision, right? So in short, for a given value of sigma square, if there is enough variation in the x values, beta 2 can be measured more accurately than when the xi do not vary significantly. So this is the reason that there is one of the assumption of ordinary least square, that there is sufficient variation in the values of the independent variable. Then another important observation, that if we increase the sample size, the number of terms in the sum of xi square will increase. So as n increases, the precision with which beta 2 hat can be estimated also increases. Actually, you can, rather than algebraically understanding this, you can intuitively understand that when we increase the sample size, then the sample is converging towards the population behavior. That is, for a given population, if we keep on increasing the sample size will start becoming similar to the population. So no matter we use the sample or the population, the estimates will be similar. So this is the reason the precision of beta 2 hat or the slope coefficient will be increased. Similarly, you can note some other concepts or facts about the variance of beta 1 hat, and that for now I leave on you. Just have a look on the formula for variance of beta 1 hat, and then you can easily understand. Now property number or feature number 3, as beta 1 hat and beta 2 hat are estimator, we know that they will vary from sample to sample. Not only they will vary, but in a given sample they are likely to be dependent on each other, because the sample is a random, the sample at hand is a random sample. So these variables will be random values, and these random values can be dependent upon each other, and we can easily measure the dependence between the intercept and the slope coefficient by using this formula. If you wish to derive the full form of this covariance, this is given in page 93 of Gujarati and Porter book. So just as an exercise, just go to page number 93, and there is a detailed derivation available for this covariance. So and by the way, if you don't have theoretical understanding of what is covariance, please watch my lecture series on introductory statistics, where I have introduced the concept of covariance. So the relevant video is, let me show you right now. The relevant video on the Rao Hub channel is, just a minute, let me go to, so this particular video titled Pearson correlation coefficient, this is uploaded in the playlist statistics lecture. Title is Pearson correlation coefficient. I will post its URL in the comment section, so you can watch this video, and that will give you an understanding of the concept of correlation and covariance that are important to understand the discussion here. Okay, so we were discussing about the covariance between the slope coefficient and the intercept coefficient, and we just proved that variance of beta 2 hat is equal to this term, so I have used this. Now we know that variance of beta 2 hat is always positive, that because by definition variance is always positive. So that means that if x bar, that is the mean of x variable, if it is a positive number, then the covariance between slope and intercept will be negative, right? If x bar is positive, then the covariance between beta 1 hat and beta 2 hat will be negative. What does that mean? If the covariance is negative, that means that if one increases, the other will decrease. That is, if the beta 1 hat increases, then beta 2 hat decreases. So it is equivalent to saying that if the slope coefficient beta 2 hat is overestimated, the intercept coefficient will be underestimated, because they are moving in opposite direction because of the negative sign. So once we cover the concept of multicollinearity in detail, we will see that this covariance formula is quite handy in some of the concepts related to multicollinearity. So thank you for watching today's video. Please subscribe to this channel. You can contact me on my official or my personal email ID, so that apart from watching the videos, we can develop a professional contact. By the way, I am a faculty member of statistics at National University of Science and Technology, Pakistan, NAST, Pakistan. So you can collaborate with me, and I hope and I wish that you find these learning resources useful. Thank you, and see you in the next video.